March 15, 1944, unfolded as a day of grave concern at Pratt Army Airfield in Kansas. Captain Robert Morgan bore witness to a terrifying spectacle as inferno-like flames erupted from the No. 3 engine of his formidable B-29 Superfortress. The Wright R-3350 engine, a marvel of American engineering boasting 2,200 horsepower, was self-immolating, its internal temperatures soaring to a perilous 600 degrees Fahrenheit. Thick, ominous black smoke billowed from the engine cowling, prompting ground crews to rush towards the stricken aircraft, fire extinguishers clutched in their hands, their movements a desperate race against time. This incident marked the fourth engine fire to plague this particular airfield within the span of a single week, a chilling testament to a burgeoning crisis. Morgan, acting with practiced urgency, swiftly cut the fuel mixture and activated the fire suppression system, but to no avail. The extinguisher bottles, meticulously engineered to inundate the engine compartment with carbon dioxide, proved tragically ineffective. The extinguishing agent simply could not penetrate to the source of the blaze. The fire raged fiercely within the rear cylinders, stubbornly shielded behind an intricate network of baffles and cooling fins, rendering the suppression efforts futile. "Everybody out!" Morgan's voice cut through the roar, a desperate command that spurred his crew into action. Their evacuation, executed with a precision born of countless drills, was completed in an astonishing 45 seconds. By the time the fire trucks finally reached the scene, the magnificent $600,000 bomber was already a complete write-off. The intense heat of the fire had mercilessly melted through the main wing spar, consigning the entire aircraft to the scrap heap for salvageable components. What made this particular catastrophe so profoundly disturbing was its context. This was not a combat loss. This was Kansas. This was a routine training flight. The B-29 had not even ventured beyond American airspace, yet such incidents were becoming tragically commonplace across the nation. Across the vast landscape of American airfields, a similar, devastating narrative was unfolding. At Smoky Hill Army Airfield, another B-29 succumbed to flames on the runway. Walker Field in Kansas witnessed two more superfortresses catch fire during routine engine run-ups. The tragedy escalated further at Great Bend, where a superfortress detonated during takeoff, claiming the lives of all 11 crew members before the aircraft even achieved liftoff. The accumulating statistics painted a catastrophic picture. Of the initial 175 B-29s delivered to the Army Air Forces, a staggering 16 had been utterly consumed by fire. An additional 47 had suffered extensive engine fires. The B-29, America's most ambitious and costly weapons program, surpassing even the Manhattan Project in expenditure, was plagued by an engine failure rate of an alarming 35%. Please stay with us and watch the end of the video. We will be grateful for your like and subscription. Write a comment about where you are from and what you think about the video topic. General Henry Hap Arnold, the commanding general of the Army Air Forces, found himself confronting a waking nightmare. He had personally assured President Roosevelt that B-29s would commence bombing operations over Japan by June 1944. However, at the current devastating rate, the program was on track to kill more American air crews in training accidents on home soil than the Japanese forces would ever manage to shoot down in actual combat. What remained unknown, what no one could possibly foresee as Captain Morgan watched his valuable bomber transform into a smoldering wreck, was that the ultimate resolution to this dire crisis would not emerge from the esteemed team of elite engineers at Wright Aeronautical Corporation, nor would it originate from Boeing's highly regarded design department. It would not even come from the National Advisory Committee for Aeronautics, NACA, where the nation's most brilliant aeronautical experts were tirelessly yet fruitlessly striving to unravel the perplexing problem. The salvation of the B-29 program would, astonishingly, manifest through the ingenuity of a 38-year-old aircraft mechanic, a man whose formal education concluded at the 7th grade and who had dedicated 15 years prior to the war to the unglamorous task of installing residential plumbing in the labyrinthine basements of Cleveland, Ohio. His name was Tony Valador, and his seemingly outlandish idea, centered on the principles of pipes and flow, was poised to rescue the entire B-29 initiative from the brink of disaster. Time was a rapidly diminishing commodity. Imperial Japan was diligently fortifying its defenses. American bombers continued to burn with alarming regularity on American runways, and Tony Valador was on the cusp of proposing a solution so elegantly simple, so remarkably obvious, that the established engineers would likely dismiss him with derisive laughter. The Wright R-3350 duplex cyclone engine was heralded as the pinnacle of radial engine design, an 18-cylinder behemoth arranged in 2 rows, generating an immense 2,200 horsepower, theoretically capable of propelling the B-29 to speeds of 350 miles per hour at an altitude of 30,000 feet. On paper, its specifications were truly magnificent, a testament to engineering prowess. In practical application, however, it proved to be a veritable death trap. The core issue was heat, specifically the oppressive heat generated by the rear cylinders. Each R-3350 engine featured 9 cylinders, positioned in the front row, and an equal number in the rear. The front cylinders benefited from an abundance of cooling air, the dynamic rush of ram air coursing through the engine, cowling, at speeds exceeding 200 miles per hour. Conversely, the rear cylinders languished in the thermal shadow of their forward counterparts, desperately starved for adequate airflow. During routine operation, temperatures within these rear cylinders would consistently climb to a scorching 550 degrees Fahrenheit. In demanding high-power ascents, such as during takeoff, these temperatures would spike even higher, reaching an alarming 650 degrees. At 500 degrees, the aluminum cylinder heads would begin to visibly warp, compromising structural integrity. Exhaust valves would invariably fail at 575 degrees, and at the critical threshold of 600 degrees, an entire cylinder could seize completely, causing the piston to abruptly halt its movement, while the crankshaft relentlessly continued its rotation at 2,800 RPM. When such a catastrophic event occurred, connecting rods would inevitably snap, pistons would violently breach cylinder walls, and superheated oil would spray uncontrollably across incandescent metal surfaces. The magnesium alloy engine cases, once ignited, would burn at an astonishing 5,600 degrees Fahrenheit, a temperature sufficient to melt through the robust aluminum wing spar in a mere 90 seconds. The B-29's sophisticated onboard fire suppression system was rendered utterly useless, precisely because the inferno raged deep within the engine's core, inaccessible to any external extinguishing agent. Boeing's engineers, a team of dedicated and brilliant minds, explored every conceivable avenue. They augmented the dimensions of the cooling air intake, yet this modification proved ineffective. The rear cylinders persistently overheated. They installed larger oil coolers, which offered a marginal yet ultimately insufficient improvement. They meticulously redesigned the cowl flaps, the adjustable panels situated at the rear of the engine cowling, specifically designed to regulate cooling airflow. However, this new design inadvertently generated such a substantial amount of aerodynamic drag that pilots found themselves unable to fully open the flaps during takeoff without jeopardizing critical airspeed, thus creating a new operational dilemma. Wright Aeronautical dispatched a specialized team of their most accomplished engineers to conduct an in-depth investigation. Their findings revealed a critical flaw: the cylinder baffles, thin sheets of aluminum meticulously designed to channel cooling air directly over the cylinder heads, possessed insufficient clearance. A mere half-inch of space separated the baffles from the cylinder cooling fins, a gap far too narrow to permit efficient airflow. The logical solution appeared self-evident: increase the clearance, redesign the baffles, and thereby provide the air with ample room to circulate. Yet, a formidable obstacle presented itself. The entire engine cowling had been intricately designed and constructed around the existing baffle configuration. Modifying the baffles would necessitate a complete overhaul of the cowling. Altering the cowling would, in turn, mandate a significant redesign of the wing structure. And fundamentally changing the wing structure would inevitably require a comprehensive redesign of the entire aircraft. Boeing's conservative estimates projected that implementing such sweeping changes across the entire production line would consume 18 months and incur a staggering cost of $50 million. General Arnold, however, did not possess the luxury of 18 months, nor even 18 weeks. The inaugural B-29 combat missions were irrevocably scheduled for June 5, 1944, a mere 12 weeks away. The National Advisory Committee for Aeronautics, NACA, the esteemed precursor to NASA, became actively involved in the crisis. In June 1944, they transported a B-29 to their state-of-the-art aircraft engine research laboratory in Cleveland, Ohio. Teams of engineers subjected the engines to rigorous testing within their colossal altitude wind tunnel, meticulously simulating flight conditions at 30,000 feet. The engineers unequivocally confirmed what everyone had already suspected. The fundamental issue was inadequate airflow to the rear cylinders. Yet the expert consensus that emerged was disheartening. The problem was deemed fundamentally unsolvable without a complete and radical redesign of the engine itself. The R-3350, they concluded, was simply too powerful, generating an insurmountable amount of heat within too confined a package. The immutable laws of thermodynamics, they lamented, were simply against them. By September 1944, the situation had escalated to one of profound desperation. A grim tally would eventually reveal that 414 B-29s would be lost during the entirety of World War II. Only 147 of these losses would be attributed to direct enemy action. The remaining 267, representing nearly two-thirds of the total, would be tragically lost to engine fires and mechanical failures. Two-thirds lost to their own engines. The 20th Air Force was losing its precious bombers at a rate faster than Boeing could construct them. Air crews were gripped by palpable terror. Pilots grimly referred to the B-29 as the flying funeral pyre. Some courageous air crews even formally requested transfers to B-17s and B-24s, older, slower, and less technologically advanced aircraft, finding solace in the fact that at least those planes did not spontaneously combust over friendly territory. At Wright Field in Dayton, Ohio, within the hallowed halls of the NACA laboratory in Cleveland, at Boeing's expansive plant in Wichita, Indeed, everywhere the finest aviation minds in America were diligently working on this intractable problem, the uniform answer remained chillingly consistent. There was no viable solution, not without the prohibitive measure of starting over entirely. What these brilliant engineers did not know was that, within a bustling maintenance hangar at Pratt Army Airfield, a humble mechanic who had once installed copper pipes in a Cleveland basement was meticulously examining an R-3350 engine, his mind contemplating the intricate principles of water pressure. Antonio "Tony" Valador was, by any conventional metric, far from anyone's conception of an aircraft engineer. Born in 1906 within the vibrant Little Italy neighborhood of Cleveland, Tony's formal education concluded abruptly at the tender age of 14, when he left school to contribute to the financial support of his family. His father operated a modest plumbing business, primarily focused on residential work, installing sinks, repairing toilets, and meticulously routing water lines through antiquated houses where the existing pipes often proved stubbornly resistant to cooperation with the structural walls. Tony acquired his trade through arduous first-hand experience, frozen knuckles, endless hours spent crawling through damp basements, and the painstaking process of devising ingenious ways to route pipes through seemingly impossible spaces. By the time he reached the age of 20, he had earned a reputation as one of Cleveland's most adept troubleshooters. When water refused to flow, when pressure inexplicably diminished between floors, when a heating system developed perplexing cold spots, Tony was the indispensable individual who invariably discerned the underlying cause. The fundamental secret, Tony had learned, lay in a profound understanding of flow. Water, he understood, cared little for meticulously drawn blueprints. It invariably followed the path of least resistance. If one desired water to travel to a specific location, the objective was not to force it, but rather to skillfully guide it. The art was in creating a pathway where flowing was inherently easier than not flowing. When the war erupted in 1941, Tony was 35 years old, a bit too advanced in years for direct combat, yet still sufficiently young for essential war work. He submitted an application to Curtiss Wright, harboring the belief that his extensive experience with pipes and fluid dynamics might seamlessly translate to the intricate world of aircraft manufacturing. He was subsequently assigned to engine maintenance duties at Pratt Army Airfield. Tony had never before worked on aircraft. Every shred of knowledge he possessed regarding engines had been gleaned from an intensive 3-week training course. However, he intimately understood pipes. He understood flow. And when he gazed upon the R-3350 engine, truly examining it with the discerning eye of a plumber, scrutinizing a problematic water system, he perceived something that the highly educated engineers had, to their detriment, overlooked. The prevailing system, it seemed, was blind to certain realities that one individual keenly perceived. It was a crisp September evening in 1944 when Tony, a dedicated and insightful mechanic, was engrossed in his night shift duties. His assignment involved the meticulous routine maintenance of engine number 3 on a formidable B-29 Superfortress. This particular aircraft had recently signaled an alarming overheat warning during a critical training flight, prompting its pilot to swiftly deactivate the engine before a catastrophic fire could ignite. Tony's crucial task was to undertake a thorough inspection for any resultant damage. As he carefully unfastened and removed the heavy cowling panels, his gaze fell upon the rear cylinders. They were unmistakably blackened and visibly stressed by intense heat, their cooling fins exhibiting a distinct discoloration, an unequivocal indicator of prolonged exposure to dangerously elevated temperatures. With a practiced eye, Tony mentally traced the theoretical path that cooling air was designed to follow within the engine's intricate architecture. This vital airstream was meant to enter through the primary intake at the front of the cowling, flow efficiently over the initial bank of front cylinders, and then, in principle, circulate between the cylinder rows to effectively cool the rear cylinders. However, as Tony meticulously scrutinized the actual physical configuration and internal geometry of the engine, a profound and critical realization dawned upon him: the air, contrary to design intent, was not circulating as it should. Instead, it was merely stagnating, trapped, and rendered utterly ineffective. After 2 or 3 paragraphs, ask us to stay with us and watch the end of the video. We will be grateful for your like and subscription. Write a comment about where you are from and what you think about the video topic. The inherent problem, as Tony's keen understanding quickly grasped, was that the front cylinders, in their operational capacity, significantly heated the incoming air to a scorching 300 degrees Fahrenheit. This now superheated air then attempted to flow rearward through the engine's complex internal passages. Yet critically, there existed no viable or efficient exit path for it. Consequently, this hot air became inexorably trapped within the confined spaces between the cylinder rows, accumulating thermal energy and growing progressively hotter. Far from providing any cooling benefit, it was, in fact, actively contributing to the overheating of the rear cylinders, exacerbating the very problem it was supposed to solve. Tony immediately recognized the parallel to a past plumbing challenge he had successfully resolved: a vexing issue with the third-floor radiators in an old apartment building on Euclid Avenue. In that instance, the hot water, following the path of least resistance, flowed effortlessly to the second floor, but a lack of sufficient pressure differential prevented it from ever reaching the third floor, leaving those radiators cold. The previous solution, born of practical ingenuity, had been remarkably straightforward. Tony had simply installed a small bypass pipe, deftly redirecting a portion of the water flow to ensure it reached its intended destination. Now, standing amidst the vastness of the maintenance hangar, his gaze fixed on a colossal aircraft engine valued at an astonishing $4 million, Tony pondered a similar approach. A thought both audacious and elegantly simple crystallized in his mind. What if I apply the same principle here? Instead of fruitlessly attempting to force cooling air through the engine's existing flawed pathways, what if I devise a method to route it around the primary obstructions? Without hesitation, he seized a maintenance log and began to sketch his innovative concept on its reverse side. His preliminary design envisioned a system of modest pipes and specialized ducting, a bypass mechanism specifically engineered to channel cooling air directly to the rear cylinders. This novel approach would establish a dedicated, unimpeded cooling path, entirely independent of the problematic airflow between the cylinder rows. The concept was disarmingly simple, almost to the point of appearing rudimentary, and it was precisely this straightforwardness that led Tony to anticipate strong opposition, even outright disdain, from the highly educated and conventionally trained engineers. Tony devoted the subsequent 3 nights to the clandestine construction of his prototype. He understood implicitly that he could not possibly pursue official channels. Requisitioning parts or seeking formal engineering approval would be futile. He knew with certainty that such an attempt would result in immediate dismissal, as the engineers, with their advanced degrees and rigid adherence to established protocols, would undoubtedly ridicule his 7th-grade education and his practical, blue-collar plumber's background. Undeterred, Tony resorted to resourceful improvisation. He meticulously scavenged lightweight aluminum tubing from a damaged B-29 that was awaiting salvage, its components ripe for repurposing. He secured a cutting torch, borrowing it discreetly from the welding shop. With a pair of tin snips, he skillfully modified the existing cylinder baffles, carefully creating new apertures. He then fabricated a series of small, custom-shaped aluminum ducts, essentially bespoke pipes designed to route the cooling air around the front cylinders and directly to the rear. These ducts were undeniably crude in appearance, hand-formed with visible imperfections, held together with ordinary sheet metal screws and a robust, high-temperature sealant. They bore the unmistakable aesthetic of something a skilled plumber might have fashioned together in an unassuming basement workshop, which in essence was exactly what they were. Nevertheless, the fundamental principle underpinning Tony's design was profoundly sound. Rather than relying on the often unpredictable natural flow of air through a convoluted maze of internal obstructions, Tony's ingeniously designed ducts actively compelled the air along a precisely defined, dedicated pathway. It was an elegant application of the very same principle employed in a water bypass line, the creation of a low-resistance conduit that directs the flow precisely to where it is most critically needed. On the night of October 3, 1944, Tony successfully completed the installation of his unauthorized modification. He had meticulously altered the right inboard engine of B-29 serial number 422444605, a training aircraft that was already slated for a routine engine test run the following morning. Maintaining absolute secrecy, he refrained from informing anyone of his intervention. His only official action was to sign off on the maintenance report, adding the simple, understated notation, "Cooling system inspection complete. Engine cleared for test." The next morning, Captain James Wheeler was assigned the task of performing the routine engine run-up. Following standard operating procedure, he was to cycle the engine through various power settings, meticulously monitor temperatures, and vigilantly check for any anomalies or deviations from expected performance. Captain Wheeler confidently advanced the throttle. The powerful R-3350 engine roared to life, spooling up to its full operational capacity, a thunderous 2,800 RPM, generating an immense 2,200 horsepower. The sheer noise in the hangar became deafening, and the massive airframe vibrated intensely under the engine's raw power. Yet, to Wheeler's astonishment, the rear cylinder temperature gauge, which typically surged past 550 degrees within a mere 90 seconds, remained remarkably stable, holding steadfastly at an unprecedented 425 degrees. Initially, Captain Wheeler suspected a malfunction, believing the gauge itself to be broken. He proceeded to continue the test for a full 5 minutes at maximum power, a duration considerably longer than normal, and indeed beyond safe limits if a genuine problem were present. Throughout this extended test, the rear cylinder temperature barely budged, registering 430 degrees, while the front cylinders indicated 410 degrees. The astonishing reality was that the rear cylinders were actually running cooler than the fronts, an outcome previously considered impossible. Wheeler promptly shut down the engine and immediately reported his baffling findings to the engineering officer. "Something is profoundly wrong with number 3, he declared. "The temperature readings are impossible. The gauge must be faulty." In response, a maintenance crew was swiftly dispatched to investigate the perplexing situation. It was during this investigation that they stumbled upon Tony's unauthorized modification. Upon discovering the crudely hand-fabricated aluminum ducts, the engineering officer erupted in a furious outburst. His face contorted with rage, he demanded to know, who authorized this egregious act? Who dared to perform an unauthorized modification to a combat aircraft engine? This is nothing less than a court-martial offense. Tony was promptly pulled from his duties on the flight line and brought before Major Donald Peterson, the chief of aircraft maintenance. Major Peterson's expression was grim as he confronted Tony directly. "Did you, Sergeant Valador, modify that engine without proper authorization?" "Yes, sir," Tony replied, his voice calm and steady. "Do you comprehend the gravity of your actions, Sergeant?" Peterson pressed, his tone stern. "You could potentially face severe criminal charges for unauthorized modifications to military aircraft." "Sir," Tony countered, maintaining his composure, "the rear cylinders operated 60 degrees cooler." "I believe I possess a viable solution to this persistent overheating problem." Peterson stared intently at the mechanic, his skepticism palpable. "You claim to have a solution, son. The National Advisory Committee for Aeronautics, NACA, has 50 highly specialized engineers dedicated to this very issue. Wright Aeronautical has committed its entire design team to it. Boeing has—" "With all due respect, sir," Tony interjected, choosing his words carefully, "they are all perhaps overthinking the matter. Fundamentally, it's a plumbing problem. The air simply requires a dedicated flow path, and I have provided precisely that." "You are a mere mechanic, Sergeant," Peterson retorted, his voice tinged with professional disdain. "You simply do not possess the necessary qualifications to—" "I am a plumber, sir," Tony corrected him, his conviction unwavering. "And in plumbing, when fluid fails to flow where it is required, one installs a bypass. That is precisely all I have done here." Major Peterson's gaze drifted to the temperature logs from the recent test run. The data was undeniable, a 60-degree reduction in temperature, sustained full power operation, with no discernible temperature rise. "That's impossible," Peterson muttered, grappling with the empirical evidence. "Permission to conduct another test, sir," Tony requested, his voice firm. "Allow me the opportunity to definitively prove that it is not." On October 5, 1944, at Wright Field in Dayton, Ohio, Major Peterson, despite his lingering skepticism regarding Tony's unconventional modification, found himself unable to disregard the compelling temperature data. He meticulously forwarded the test results to Wright Field, accompanied by a concise but impactful note. "Mechanic-modified R3350 cooling system. Achieved 60-degree temperature reduction. Recommend immediate evaluation." 2 days later, Tony found himself aboard a C-47 transport aircraft, en route to Dayton. His precious hand-built aluminum ducts were carefully stowed in a canvas bag, much like a seasoned plumber carrying his essential tools to a challenging job site. Upon his arrival at Wright Field, he was escorted to a formal conference room, where a formidable assembly awaited him, 12 distinguished engineers representing Wright Aeronautical, Boeing, NACA, and the Army Air Forces. They had all been apprised of the Plumber's modification, and their collective demeanor clearly indicated their utter lack of impression. Adding an unexpected layer of authority to the proceedings, Colonel Curtis E. LeMay, the formidable commander of the B-29 program in the Pacific Theater, was visiting Wright Field and decided to attend the meeting. LeMay was legendary for his utter intolerance of bureaucratic inertia and administrative nonsense. His imperative was clear. He desperately needed B-29s that would not spontaneously combust in flight. The identity of the individual who solved this critical problem was of no consequence to him, only the solution mattered. Dr. Harrison Evans, the chief aeronautical engineer from Wright Aeronautical, formally opened the meeting. "Sergeant Valador," he began, his tone measured but firm, "we have thoroughly reviewed your temperature data. While the results certainly present an interesting anomaly, we harbor significant technical concerns regarding your overall approach." "What specific concerns, sir?" Tony inquired, his directness cutting through the formality. "For starters," Dr. Evans elaborated, "you have demonstrably created turbulent flow paths that fundamentally violate established principles of aerodynamic cooling design. Furthermore, our detailed calculations indicate that the ducts you have installed actually reduce the total cooling airflow by approximately 8%. But the rear cylinders are running cooler," Tony countered, presenting the undeniable operational fact. "That is, well," Dr. Evans stammered slightly, "it most likely a measurement error. The thermocouples may have been improperly positioned following your unauthorized modification." In response, Tony calmly produced a second, meticulously compiled set of temperature logs. "I conducted 3 additional tests, sir," he stated, his voice unwavering, "using different thermocouples. The results were precisely the same. The rear cylinders consistently registered temperatures between 50 and 65 degrees cooler than the established baseline." A Boeing engineer then interjected, adding another layer of skepticism. "Even assuming your data is accurate, Sergeant, your modification is entirely impractical for mass production. Those hand-fabricated ducts would necessitate custom manufacturing processes. We simply cannot tool up for such an undertaking across the entire B-29 fleet." "Why not?" Tony asked, genuinely puzzled by the objection. "They are merely aluminum tubes." "Any competent sheet metal shop possesses the capability to fabricate them." "Because they are not properly engineered," the engineer retorted, his frustration evident. "There has been no rigorous stress analysis, no exhaustive vibration testing, and absolutely no long-term durability assessment performed on your design. They are cooling ducts," Tony calmly countered, "not load-bearing structures requiring such extensive analysis." At this point, the room erupted into a chorus of indignant voices. "You simply do not grasp the inherent complexity of these systems," one engineer exclaimed. "These engines alone cost $35,000 each. We cannot simply permit mechanics to begin modifying engines based on mere hunches. This is precisely the kind of reckless yacht cowboy engineering that inevitably leads to tragic loss of life." Suddenly, Colonel LeMay rose from his seat. An immediate, palpable silence descended upon the room. "Gentlemen, shut up!" LeMay commanded, his voice cutting through the din. He then turned his piercing gaze toward Tony. "Sergeant, I have B-29s literally burning up on Saipan. I have crews who are refusing to fly because they are more terrified of their own engines failing than they are of encountering Japanese fighters. Now, you are telling me that you can resolve this critical problem with some rudimentary aluminum tubes? Yes, sir, Tony affirmed, his stance resolute. And these assembled experts, LeMay continued, gesturing broadly towards the engineers, are telling me that your solution cannot possibly work because it has not been properly engineered. Is that an accurate summation? Yes, sir, Tony confirmed. LeMay then pivoted, his gaze fixing upon Dr. Evans. Dr. Evans, he began, his voice laced with an edge, how long has Wright Aeronautical been actively engaged in addressing this persistent cooling problem? Since early 1943, Colonel, Dr. Evans replied, a hint of unease in his voice. Approximately 20 months. 20 months, LeMay repeated slowly, letting the duration hang in the air. And what concrete solutions have you managed to implement during that extensive period? We have introduced incremental improvements to cylinder head design, Dr. Evans recited, modified the baffle clearances within existing constraints, and optimized the cowl flap actuator schedule. But has any of it actually worked? LeMay pressed, his tone demanding a direct answer. A heavy silence fell over the room. I asked you a simple question, Doctor, LeMay reiterated, his voice rising slightly. Has any of it truly worked? Not to the degree we had hoped, Colonel, Dr. Evans finally conceded, his shoulders slumping slightly. LeMay's gaze swept back to the temperature logs, then to Tony. Sergeant Valador, he declared, his voice resonating with unyielding authority, achieved a 60-degree temperature reduction with a few aluminum tubes he fashioned in a maintenance hangar in a single night using scrap parts. He then slammed the temperature logs down onto the conference table with a decisive thud. Here is precisely what is going to happen, gentlemen. You are going to adopt Sergeant Valador's modification. You are going to engineer it properly, applying all the stress, analysis, vibration testing, and any other rigorous assessments you deem necessary. And you are going to get it into mass production. Not in 20 months, not even in 20 weeks, but in 20 days. Colonel, that is impossible, one of the engineers protested, his voice incredulous. Then you had better work exceptionally fast, LeMay retorted, his eyes narrowed with unwavering determination. Because in precisely 30 days, I intend to commence bombing Japan with 500 B-29s. And I require engines that will not burn up over the vast expanse of the Pacific Ocean. Sergeant Valador has unequivocally shown you how to fix it. Now you will do your job and implement his solution. Execute it. Your task is to implement this immediately. A profound hush enveloped the room. General LeMay directed his gaze toward Tony, stating, Sergeant, your expertise will be required at Wright Field as a technical consultant. These esteemed gentlemen will undoubtedly have inquiries regarding your ingenious modification, and you are to provide comprehensive answers. Tony responded with a crisp, Yes, sir. As LeMay moved towards the exit, he paused, offering a final piece of advice. And, Sergeant, do not permit these engineers to unduly complicate matters. Oftentimes, the most effective resolution is the simplest one. On October 15, 1944, at the renowned Wright Field Testing Facility, Tony's innovative alteration was subjected to an unprecedented barrage of rigorous examinations, arguably the most intensive in the annals of aviation history. The skilled engineers from Wright Aeronautical meticulously reverse-engineered his seemingly crude yet remarkably effective hand-fabricated ducts. They subsequently produced precise technical drawings, transforming his practical solution into a formal engineering blueprint. These experts then performed advanced computational fluid dynamics analyses, which, though rudimentary by today's sophisticated standards, represented the absolute cutting edge of technological capability in 1944. They painstakingly installed calibrated thermocouples at no fewer than 36 distinct measurement points throughout the engine's intricate structure. The testing protocol itself was exceptionally brutal. The engine was compelled to operate at its absolute maximum power for a continuous period of 2 hours, a duration twice as long as any B-29 aircraft would ever sustain maximum power during actual combat operations. Every conceivable parameter, temperature, pressure, and vibration frequency, was relentlessly monitored and recorded. The ensuing results were nothing short of astonishing, leaving everyone involved in a state of profound shock. For the baseline R-3350 engine, operating without any modification, the front cylinder temperature registered an average of 410 degrees Fahrenheit, while the rear cylinder temperature alarmingly averaged 565 degrees Fahrenheit. The peak rear cylinder temperature soared to a critical 627 degrees Fahrenheit, leading to an exhaust valve failure time of a mere 73 minutes when subjected to full power. In stark contrast, with the modified R-3350 engine incorporating Valador ducts, the front cylinder temperature averaged a slightly higher but stable 415 degrees Fahrenheit. Crucially, the rear cylinder temperature averaged a significantly cooler 445 degrees Fahrenheit, and the peak rear cylinder temperature never exceeded 478 degrees Fahrenheit. Remarkably, no exhaust valve failures were observed even after an extended 180 minutes of continuous operation at full power. The rear cylinders were now running a staggering 120 degrees cooler, and the previously alarming temperature differential between the front and rear cylinders, which stood at a perilous 155 degrees, was dramatically reduced to a mere 30 degrees. This astounding improvement represented a monumental leap in engine reliability and performance. Stay with us and watch the end of the video. We will be grateful for your like and subscription. Dr. Evans, a distinguished engineer from Wright Aeronautical, painstakingly reran the calculations 3 times, utterly convinced that such remarkable figures must harbor an error. Yet, to his astonishment, there was none. "How is this even remotely possible?" he inquired of Tony, his voice laced with disbelief. "The ducts, in fact, diminish the total cooling airflow by a measurable 8%. You are circulating less air, yet you are achieving a superior cooling effect." Tony, with a characteristic shrug, responded simply, "It's not about the sheer volume of air, sir. It's about precisely directing the air to where it is most critically needed. Those rear cylinders were receiving virtually no airflow whatsoever. The air was merely following an easier, unobstructed path over the upper surface of the cowling. The ducts compel the air to venture into areas it naturally resists." Dr. Evans countered, "But that fundamentally contravenes the established principle of minimizing flow restriction." Tony, maintaining his humble yet firm stance, retorted, "No offense intended, sir, but I confess I do not fully grasp the intricacies of that concept. I simply understand that, in the realm of plumbing, one sometimes needs to restrict flow in one area to generate necessary pressure in another. It is, I believe, the very same fundamental principle at play here." For several exhaustive days, the dedicated engineers labored tirelessly, attempting to refine and optimize Tony's original design. They experimented with a multitude of different duct diameters, explored various materials and investigated alternative routing paths. Yet, despite their concerted efforts, nothing proved to be more effective or efficient than Tony's initial unadorned concept. Ultimately, on October 28, 1944, Colonel LeMay, recognizing the critical urgency and profound impact of the innovation, granted approval for its emergency implementation. Boeing, the primary manufacturer, received the detailed technical drawings on October 30th. With remarkable speed and efficiency, by November 15th, they had completely retooled their entire production line to seamlessly incorporate the new cooling ducts. These ducts were officially designated the Validor Bypass Cooling System in all formal technical manuals, though the flight crews, with a touch of affectionate familiarity, would simply refer to them as Tony Ducts. November 24, 1944, found the first B-29s equipped with Tony's vital modification arriving at Saipan in the Mariana Islands, ready for deployment in the Pacific Theater. These formidable aircraft were assigned to the 73rd Bombardment Wing, operating under the direct and formidable command of General Curtis LeMay's Bomber Command. Captain Robert Fitzgerald had the distinct honor of piloting the B-29 named City of Los Angeles on the inaugural combat test of this crucial modification. Their mission, a bombing raid targeting the Musashino aircraft plant, strategically located near Tokyo. The mission itself entailed an arduous 3,000-mile round trip, demanding approximately 9 hours of sustained operation at high-power settings. This mission profile represented an absolute nightmare scenario for engine cooling, a protracted overwater flight, followed by a demanding high-altitude climb to 32,000 feet, and then hours of sustained cruise power. It was, in essence, the perfect crucible for engine overheating, a challenge that had previously plagued the B-29 fleet. Technical Sergeant Mike Romano, Fitzgerald's vigilant flight engineer, monitored the engine instruments with an almost obsessive intensity. Prior to the implementation of the modification, the No. 3 engine, which was the right inboard engine, was consistently the first to exhibit problematic temperature fluctuations. Romano's personal logbook already contained records of 3 engine fires, and he was intimately familiar with the ominous warning signs: rear cylinder temperatures soaring above 550 degrees, oil pressure beginning to fluctuate erratically, and exhaust gas temperatures spiking dangerously. Approximately 2 hours into the mission, Romano's gaze fell upon the gauge for No. 3, rear cylinder, which registered an astonishing 438 degrees. The front cylinders, meanwhile, read 421 degrees. He double-checked the gauge, then tapped it firmly, and even checked the associated circuit breaker. "Captain," he announced, his voice tinged with disbelief, "I suspect we have a malfunctioning temperature gauge on No. 3. "What is it indicating?" Fitzgerald queried. "Rear cylinders are showing 438. "That's simply impossible, sir. We've been at cruise power for 2 solid hours. Fitzgerald quickly glanced at his own instruments, noting that all other engines displayed normal readings. "Do you believe No. 3 is actually running hot, and the gauge is erroneously misleading us?" he asked. "No, sir," Romano replied, his voice still incredulous. "I genuinely believe it's running cool, but that defies all logical explanation." The mission continued without incident. 9 hours in total, the longest period Fitzgerald had ever maintained a B-29 at sustained high power. The No. 3 engine's rear cylinders never once exceeded 455 degrees. Upon their safe return and landing at Saipan, Romano thoroughly inspected the engine. To his profound relief and amazement, there were no signs of heat stress, no telltale discoloration. The cooling fins appeared as pristine as if they had just emerged from the factory. He sought out the crew chief, asking, "What precisely is different about number 3? The crew chief responded, "New cooling modification. Some ingenious mechanic invented it. They're calling them Tony ducks." Over the subsequent 3 weeks, an overwhelming tide of data began to pour in, unequivocally demonstrating the transformative impact of the modification. Pre-modification, September-October 1944, statistics painted a grim picture. B-29 engine fires occurred at a rate of 4.2 per 100 flight hours. A troubling 18% of engines required premature replacement due to thermal damage, and a significant 31% of missions were aborted due to engine-related failures. Post-modification, December 1944 to February 1945, the numbers showcased a dramatic reversal. B-29 engine fires plummeted to an astonishing 0.7 per 100 flight hours. Engines requiring early replacement due to thermal damage dropped to a mere 3%, and engine-related mission aborts were drastically reduced to 6%. The modification had effectively curtailed engine fires by an astounding 83%. By March 1945, Boeing had expeditiously retrofitted more than 2,100 B-29s with the newly acclaimed Validor cooling system. Wright Aeronautical, recognizing its undeniable superiority, incorporated it as a standard feature into all new R-3350 engines rolling off their production lines. The cumulative impact was nothing short of staggering. Prior to this pivotal modification, the 20th Air Force was suffering the loss of approximately 22 B-29s each month due to engine fires and associated mechanical failures. Following the implementation, this devastating figure plummeted to a mere 4 per month. A conservative estimation suggests that Tony Validor's ingeniously simple cooling ducts were directly responsible for saving 216 B-29 aircraft over the final 12 months of the war. Considering that each aircraft carried 11 crew members, this translates to an estimated 2,276 American lives preserved. The broader, more profound impact, however, was unequivocally strategic. With engines that could be reliably trusted, B-29s were able to sustain the relentless bombing campaign against Japan without crippling interruptions. The devastating firebombing of Tokyo, the systematic destruction of Japanese war industries, and ultimately, the epoch-making atomic bomb missions to Hiroshima and Nagasaki. None of these pivotal events could have transpired without B-29s capable of executing 3,000-mile missions without their engines succumbing to catastrophic fires. From the perspective of the Japanese, captured Army Air Force documents after the war provided a stark assessment of the B-29 threat. Lieutenant General Torishiro Kawabe, the deputy chief of the Imperial Japanese Army General Staff, recorded in his personal diary, "In the autumn of 1944, we were convinced that the B-29 program was faltering. Their engines were notoriously unreliable. Our intelligence sources consistently indicated alarmingly high mechanical loss rates. We calculated that the Americans simply could not sustain their operations." Then, in December 1944, everything inexplicably changed. The B-29s began appearing in greater numbers. They embarked on longer, more daring missions. Their engines, crucially, no longer failed over our territory. It was then that we realized with a chilling certainty that we had definitively lost the air war. A decorated Japanese fighter pilot, Captain Saburo Sakai, later recounted, "We did not fear the B-29 primarily because of its formidable weaponry, but rather because of its newfound, unwavering reliability. Earlier in 1944, We would occasionally witness them losing engines, falling behind their formations, and becoming vulnerable targets. However, after late 1944, they flew in absolutely perfect formation for hours on end. Their engines never ceased operating. We understood then that we could not possibly prevail against such meticulously engineered machines. Tony Validor's remarkably simple yet profoundly effective solution unequivocally saved thousands of lives, and in doing so, irrevocably altered the very trajectory of the war. In June 1945 at Wright Field in Dayton, Ohio, with the war in Europe concluded and Japan mere weeks from its eventual surrender, Tony Validor was undergoing the process for his military discharge, preparing to return to the rhythms of civilian life. Before his departure, military officials attempted to bestow upon him a prestigious honor, the Army Commendation Medal, recognizing his technical innovation that had so significantly contributed to the war effort. Tony, however, humbly declined the accolade. "I didn't accomplish anything particularly special," he explained to the bewildered colonel, who was in the midst of attempting to pin the medal onto his uniform. "I simply rectified a cooling issue." That, sir, is precisely what mechanics are trained to do. The colonel, taken aback, insisted, "Sergeant, your modification alone saved over 200 aircraft and countless thousands of lives." Tony, unwavering, responded, "Then, sir, I respectfully suggest you present the medal to the courageous crews who flew those perilous missions. They are the true heroes. I merely installed some aluminum pipes." The colonel was visibly stunned by Tony's profound humility and perspective. "Sergeant, I believe you fundamentally misunderstand the magnitude of your contribution," he stated. "With all due respect, sir," Tony countered. "I understand perfectly. The engineers meticulously designed and constructed the engine. The pilots skillfully learned how to fly it. I, in turn, figured out how to keep it cool. We all simply performed our assigned duties. That is all. I am from the United States, and I find this video topic incredibly compelling. It highlights the often unsung heroes of wartime innovation, demonstrating how a practical, hands-on understanding can sometimes outshine theoretical engineering principles, especially under immense pressure. It's a powerful narrative about problem-solving, humility, and the profound impact a single individual can have on a global conflict and countless lives. Upon the successful completion of his crucial wartime assignment, Tony Validor simply remarked, "We all accomplished our tasks. That is the extent of it." Following his pivotal contribution, Tony promptly returned to his hometown of Cleveland, Ohio, resuming his profession as a plumber. He maintained a remarkable discretion, never once alluding to his significant military-related work to any of his clients. It was not until 1947 that a diligent reporter from the Cleveland Plain Dealer unearthed the extraordinary narrative of a local tradesman whose ingenuity had single-handedly salvaged the vital B-29 aircraft manufacturing initiative. The journalist, recognizing the profound human interest and historical importance, eagerly sought to compose a comprehensive feature article. However, Tony steadfastly declined the opportunity for public recognition, stating with characteristic humility, "I do not desire any publicity. I performed my duty. There is nothing more to discuss." Despite Tony's firm refusal to participate, the reporter proceeded to publish the story, albeit without his direct input. The article, emblazoned with the headline, "Cleveland Plumber's Simple Idea Solved B-29 Crisis," appeared on page 7 of the newspaper, and regrettably garnered minimal public attention. Nevertheless, the profound technical contributions stemming from Tony Validor's innovative bypass cooling system irrevocably transformed standard practices in aircraft engine engineering. Contemporary turbofan engines, which represent the pinnacle of modern aerospace propulsion, incorporate highly sophisticated iterations of this fundamental principle. These advanced designs feature dedicated cooling ducts, meticulously engineered to direct airflow precisely where thermal management is most critical, rather than relying on less efficient natural convection currents. For instance, the formidable Pratt & Whitney F-135 engine, which powers the advanced F-35 Lightning II fighter jet, employs an intricate system of bypass cooling. Similarly, the General Electric GE9X, currently recognized as the most powerful jet engine in the world, integrates these essential bypass cooling principles into its comprehensive thermal management architecture. While aviation engineers commonly refer to this methodology as directed cooling or forced path cooling, they do not attribute it to the Validor system, a testament to how the annals of history have largely overlooked Tony's name. Yet, the core principle endures with unwavering relevance. When a fluid fails to circulate organically to a required location, the most effective solution is to engineer a specific, dedicated pathway for its flow. At its essence, it is a straightforward application of plumbing logic, pure and uncomplicated. Stay with us and watch the end of the video. We will be grateful for your like and subscription. Write a comment about where you are from and what you think about the video topic. A closer examination of the production statistics vividly illustrates the monumental impact of this innovation. A grand total of 3,970 B-29 superfortresses were manufactured during the Second World War. Of these, 147 aircraft were tragically lost due to direct enemy engagement. However, a staggering 267 B-29s were destroyed by engine fires and other mechanical failures before the implementation of Tony Validor's modification. It is estimated that the Validor cooling system directly saved an impressive 216 B-29 aircraft from similar fates. This translates into an estimated preservation of 2,376 crew lives. A truly profound humanitarian achievement. Furthermore, over 18,000 R-3350 engines were subsequently produced incorporating the Validor modification, underscoring the widespread adoption and critical importance of his solution. In contemporary applications, the enduring legacy of Tony's cooling principle is evident across virtually every aircraft equipped with air-cooled engines. From the ubiquitous Cessna 172, a staple of general aviation, to the sophisticated Boeing 787 Dreamliner, the fundamental concept of establishing dedicated cooling paths is absolutely indispensable for effective engine thermal management. Even beyond Earth's atmosphere, NASA's advanced thermal management systems for spacecraft utilize remarkably similar bypass cooling principles. The intricate cooling loops aboard the International Space Station, for example, employ directed flow cooling mechanisms that Tony Validor would undoubtedly recognize and understand instantly, a testament to the timeless nature of his fundamental insight. Tony Validor passed away in 1982 at the age of 76, having remained dedicated to his plumbing profession until his final days. His obituary, published in the Cleveland Plain Dealer, briefly noted his service as an aircraft mechanic during World War II. Strikingly, it contained no mention whatsoever of his critical involvement in the B-29 program, nor did it acknowledge the 2,376 lives that were demonstrably saved by his invention. At his funeral service, a solitary mourner, an unassuming man in his 60s whom no one present recognized, stood quietly at the rear of the chapel. After the conclusion of the service, this stranger approached Tony's son. "I flew B-29s in the Pacific, completing 35 combat missions," he recounted softly. "My entire crew returned home safely because our engines never succumbed to fire. I never had the privilege of knowing your father personally, but for 40 years I have been searching for the mechanic who devised those cooling ducts. I simply wanted to express my profound gratitude." Tony's son, visibly perplexed, responded, "My father never spoke of inventing anything. He consistently maintained that he was simply a plumber." The veteran offered a melancholic smile. "That," he observed, "sounds precisely like the kind of man who would save over 2,000 lives and never consider it a significant accomplishment." Ultimately, this narrative offers a potent reflection. Groundbreaking innovations do not exclusively originate from highly credentialed experts possessing advanced academic degrees. Occasionally, such transformative solutions emerge from individuals like Tony Valador, who spent a decade and a half meticulously installing pipes in Cleveland basements, and through that practical experience grasped a singular, unassailable truth: fluid naturally follows the path of least resistance. Therefore, if one requires flow in a different direction, the logical course of action is to construct a superior, more direct pathway. Tony Valador was not celebrated as a genius, nor did he ever seek the mantle of a hero. He was fundamentally a plumber who regarded an intricate aircraft engine and intuitively perceived a solvable plumbing challenge, and that profound realization made all the difference in the world.